All right, welcome to today's lesson on the programming process, where we are going to be looking at how to take the problem-solving process from a couple of days ago and apply it into the world of creating computer programs. Now, fortunately for us, the steps are fairly similar to the ones we saw in yesterday's problem-solving process. In both cases, we're going to start by defining the problem, figuring out what it is our program is all about. From there, in the programming process, we're going to follow up by doing the planning the solution stage. This stage actually incorporates 3 stages from the problem-solving process. We do the analyze the causes, developing the plans, and evaluating the solution, all in this stage. Once we've done that, we can start coding the program. This stage is similar to the implement the solution stage from our problem-solving process. And finally, we wrap up by doing the testing the program or the follow-up. This is where we make sure that our program is actually going to function the way we designed it to. There's one more stage in the programming process that didn't exist in the problem-solving process, and that is documentation. This particular stage is incorporated in every stage throughout the entire process. So we're going to do some documenting in the defining the problem, while planning the solution, while coding, and while testing. So let's take a look at each of these stages in a little bit more detail. We'll start by defining the problem. In this case, we're going to start by asking ourselves 4 big questions. The first question is, what is the purpose of this particular program? What are we trying to do? What is this program out to do? Is it converting from Celsius to Fahrenheit? Is it keeping track of all of our contacts in our contact list, etc., etc.? To do that, we need to know what information we require from the user. This is called input. So what do we need to know? Do we need to know names? Do we need to know numbers? Do we need to know tax amounts? Do we need to know whatever so that our program can calculate the results it needs? After that, we need to find out what is output to the user. What is the final result that our program is going to produce? And then lastly, our final big question is, what is the formula or algorithm that we're going to be required to get us to our output? So are we going to be using a conversion formula? Are we going to be sorting records alphabetically or numerically, right? All those kinds of things that would get us from our input to the final results of the output. Once we know that, we can begin to plan how we're going to go about solving this particular problem. And this is done using design tools. There are 2 design tools that we could use. The first is called a flowchart, and that's what we're going to be focusing on in this course. And that is a visual representation of the flow of the program. It gives you an idea of what order you're going to process your steps in. There's also something called pseudocode, which is basically a verbal version of the computer program, where it sort of says logically we're going to do this step, this step, this step, but there's no actual command or code in that particular logical structure. You can also perform some desk checking. So once we've written our flowchart or pseudocode, we can walk through the design to make sure logically it makes sense and we're not missing any steps, or they're not done out of order. And then after you've done some desk checking, you might do some peer reviews where you get some other people, your bosses, your other programmers, to step through your steps of your logic as well before you spend the time to actually code it. So flowcharts. This is what we're going to be doing in grade 10. We're used to give a graphical preview of the flow of the program. And there are some signs that we need to use to do this. The first symbol is the start and end. It's an oval. Okay, an oval for starting the program, an oval for ending the program. From there, we have an arrow to show the direction of flow of how our program is going to go, and a rectangle, which is going to incorporate any kind of process or calculation that has to occur in the program. And then to identify any input and output, we're going to use a parallelogram. So input from the user or output to the user. So an example of what this might look like. Okay, we have a program, we need to add 2 numbers together and output their sum. So we'd start with our oval, we'd input number 1, we'd input a second number, then we would do our calculation, so our sum is going to be equal to the first number plus the second number. We're going to output the results to the user, and then end our program. Okay, you can see the arrows, how the arrows are showing the direction of flow from one step to the next. Once we've planned out what our solution is going to look like, we can then move to coding the program. This is where you translate your algorithm into a formal programming language. There's a whole bunch of languages you could use: Visual Basic, C++, Turing, Pascal, Java, Python, all those different languages. In this course, we're going to focus on Alice and on Python. Once you've written your code, you're going to test it to make sure it works properly. The first step of doing this is using what's called a compiler. This is a program in the computer that is going to check your code for syntax errors. A syntax error is an error in the way the code is written. So I've misspelled something, or I'm missing a bracket or a semicolon, okay? Or I'm trying to use a variable that I haven't created yet. Okay, these are all errors in the way that code's written. It prevents the code from running at all. Once the code runs, we need to go through a debugging process. This is where you as a programmer or as a peer would run the program through using data that's going to test a variety of situations to make sure we get the correct results. It's important that you don't just test it once, because if you just test it for one scenario, it might work for that scenario, but for other scenarios, it doesn't work. So you want to test extreme answers. So a low number, a high number, numbers on the boundaries of different things you're trying to test for, and so on. This detects logic errors, or errors in the way that the program works. It works properly, but it's not giving us the results that we want. So for example, 4 minus 2 equals 3, right? It'll give us the wrong answer. That's a logic error. We got to say, okay, why is the code giving us the wrong answer? Once your program works functionally, you need to make sure you have taken care of the last stage throughout. Again, so this happens in all stages. We're going to be doing problem definitions, so making sure you understand exactly what it is your program is supposed to do. You create a plan so that all of your coders know how they're supposed to follow through in their code. You write comments within your code to make sure that your code is explainable to other programs and yourself if you ever have to go back to edit or modify your code at a later date. All of your testing procedures need to be written down, so you have some sort of documentation of what went wrong exactly, so you know how to recreate those errors, so you know how to fix those errors. Any menus, so these would be documentation for the user to use within your program itself if they get stuck, and a user's manual if they need some sort of other documentation outside of the program itself to figure out how to run your program. That's it. That's all we have time for today. We'll see you in class tomorrow where we can practice what we've learned.